Okay, so the content of today's exercise sessions are first distributions and Frobenius theorem, and secondly there will be tensors, so tensor calculus. Okay, let's start with distributions and Frobenius theorem. Okay, so first of all, let's have some um, preliminary definitions. A distribution of rank k on M. Now M is a smooth manifold, right? What is this? Can anyone give me a definition? Anyone?
So subbundle of the tangent bundle.
Okay. So sub bundle of the tangent bundle. Okay, maybe I should write subbundle D of the tangent bundle Tm. So let's recall briefly what that means. It means that D under Tm is an embedded submanifold such that dp, which is defined as d intersected with tpm, is a vector space of dimension k. Okay, so note that these aren't any kind of distributions that come from probability. Also note that these aren't any kind of distributions in the sense of generalized functions from your PDE course. These are distributions in analysis on manifolds theory. Okay, so, and furthermore, we define what an integral manifold of D is. It's an immersed submanifold in M. Let's denote it N, such that the tangent space at an arbitrary point of this manifold is equal to the vector space dp, right? So such that Tpn equals dp for any p in n. And we say that a distribution D is integrable if what holds? Can anybody recall?
If each fiber is if for every point there is a immersed manifold, the integral manifold for the distribution.
Yeah, so this set in symbols, this would be if for any point P in M, there exists an integral manifold let's call it let's call it M with P integral manifold N of D, right? Should be written here, of D with P in N. Okay, so simple example. A vector field X on your manifold determines a distribution let's denote it D of X, defined by, of course, in the obvious way, D of X at point P should be nothing else but the linear span of X at point P. So why is this smooth? Why is this like why does the why is the distribution D of X smooth in the sense of being an embedded submanifold in TM, etc.? Hint, there's a lemma.
Well, yeah, because of the the section lemma. The vector field gives us the section that spans that spans the fiber at every point.
Okay, so do you see that I forgot to add an assumption on X?
Well, yeah, it should be smooth.
Okay, that's already in the assumption. It's a vector field. But does it necessarily span the fiber? The fiber. Does it necessarily span anything of dimension 1 at point P?
Well, I guess not.
Yeah, it doesn't necessarily, because it may be 0 at a point, right? So additionally, here you should write which is everywhere non-zero. Okay, otherwise you would have like at point P, your D of X would be a one-dimensional space, and at some other point it would be a zero-dimensional space. Hence, it can't determine a distribution of constant dimension at each point, right? Okay, so but nevertheless, we have by the subbundle characterization lemma that this is indeed a subbundle, right? So um, and this lemma was given a few exercise sessions ago, so you should um, I don't know, revisit it if you can't recall what it said. Um, but X is the appropriate section of the vector bundle to take when using this subbundle characterization lemma. Okay, well, is this an integrable distribution, d of X? What do we say? Is it integrable?
Yeah, probably if we take the flow of the vector field.
Yeah,
when we
the integral curves will do. So yeah, this is an integrable distribution. Since for any point P in M, the integral curve gamma px starting at P I mean, not the integral curve, but the image of the integral curve is an immersed submanifold in M, hence determines by assumptions of what it means to be an integral curve, like it supplies us with the integral manifold. And it obviously contains P, right? Okay, well, furthermore, we have another definition. It says it's the involutivity. So D is involutive if for any two smooth sections X and Y that are smooth sections on D, also their commutator X comma Y is a smooth section. of D. So xy from smooth sections on D implies xy commutator is a smooth section on D. So now we have the main theorem that states, so this is Frobenius. It states that a distribution D on M is integrable if and only if involutive. And why is this a very nice theorem? Is because integrability condition is hard to check, and this one is easy to check. In most cases. Well, okay, so this is the preliminary definitions. And now we'd like to, of course, go and solve some exercises. And so let's do it. Let's have the following vector fields on r to the power of 3. Z partial x plus x partial z is the first one. The second one would be y, which is z partial y plus y partial z. And the last one is minus y partial x plus x partial y. Okay, and we limit ourselves to the manifold xyz from r to the power of 3 that have z greater than 0. Okay, so and what we do is we define D, or sometimes written D of x comma y. We define this as a soon-to-be distribution. This joint union P runs through all of M, and we take the linear span of the vector fields xp and yp. So our task now is to prove that D is a distribution on M that is integrable. Also, find its integral manifolds. So, any ideas on how to prove that this is indeed a distribution?
Maybe we can show that the commutator of that x and y are in involution, and then they have a
First of
integral
all,
manifold.
to be a distribution.
Yeah, that's what I'm thinking. So if we prove that they're in involution, we can integrate them to a smooth manifold, and then we
No,
can
you're
take its
checking
tangent.
involutivity already. We
They
don't
can't.
have to prove involutivity. We just have, at first we just have to show that it's a distribution.
I'm going off the Wikipedia definition here. Do we check that we have like vector fields that
Okay.
can express our D distribution?
Okay, so is that any different from the simple case here where we utilized the subbundle characterization lemma?
No.
It's the same. So D is a distribution by the subbundle characterization lemma. Okay, so now Jaakko, what was your idea? How do we prove that it's integrable?
To show that they're in involution.
Okay, so you want us to go and compute the commutator, right? So let's tell the world what we're doing by writing this dashed lines here. Okay, so x comma y, the local formula for the commutator is x evaluated on yi minus y evaluated on xi and partial I. This is by, of course, the summation convention, right? So what we get here now is, first of all, the x component of our vector field y is 0, and the x component of our vector field x is z, right? So what we get here is just y, okay? And here I should have partial x. The next one is then, so the y component of the vector field y is z, okay? And I should use my vector field x on this function z, and what I get is x minus, and now I have a 0 because the y component of my vector field x is 0, right? Partial y here. And finally, I have the z component of my vector field y, which is the function y, and minus y evaluated on the z component of my vector field x. This is here. So, but these two are 0, right? Because the vector fields, the vector field x doesn't include like the partial y or whatever. So this is nothing else but z. So did we prove involutivity?
Yes.
No.
Oh, we need to also do for all the other combinations then?
Sorry?
Do we also need to do every other combination of x, z, y?
No, we don't have to. We just have to show that. So we just want to show that this is equal to a times x plus b times y for some functions a and b. So this is what we want to show. Okay, I'm going to delete this because it doesn't make sense at this point. Was there a suggestion on how to do it or whatever?
Just multiply x by y and y by x and then subtract.
Yeah. Okay, that would be one idea. But now, okay, so first of all, I'm going to write here again the minus y partial x plus x partial y. Okay, so this is of course what we have written above, but in a nicer way. Okay, so actually what we need to do now is we need to express partial x and partial y in terms of vector fields x and y. Okay, so that what Jaka suggested would be one way, but this is kind of straightforward here. So partial x in our case is nothing else than 1 over z times vector field x minus x over z partial z, and also we have partial y is equal to 1 over z vector field y minus y over z partial x. Okay, so and if we plug this in now, note that it's possible to divide for me with z, right? Because I'm on M. So M is z greater than 0. Okay. So what I got here now is minus y over z times x plus xy over z times partial z and plus x over z y and minus xy over z partial z. And now we have that these two cancel out. Okay, so this is now yeah, this is now just minus y over z times x plus x over z times y. So hence our distribution is involutive. So by Frobenius integrable. So the next and the hardest part of this exercise is to find the integral manifolds, right? Any ideas on how to do it?
Maybe just calculate the flows and That's it.
Okay, how are you going to help yourself with the flows in order to get to integral manifolds?
You start at some point and then you just flow it to all possible places that are defined.
Okay, that's one possibility. We're going to do
I don't understand something here. Usually when we're solving differential equations, we have equations, right? But here we just have two things. There's no equality. How do we solve this?
sorry?
There's no equality. There's no
Equality between
thing. There's nothing we're solving. We just have two definitions. What are we doing?
We have vector fields. Vector fields can be interpreted in the dynamical systems way in terms of differential equations or systems of differential equations.
So maybe to solve it, we should first put it into that system of differential equations.
Okay, but we don't have to solve it to check that they can be, to check that this distribution is integrable. So yeah, this is the general theory. If you have like problems with understanding the general theory, I suggest you to read. We can do all the theory here. I suggest you to visit lectures and read Lee's book. That would be my suggestion for you. Okay, so integral manifolds. One way has been already said. It's by using flows of vector fields x and y. Okay, so another way would be what? Can anybody see it? Yeah, well, another way is a little bit trickier, and we're gonna do it first because it's because it's the easier way. Okay, so first let's write here two ways. One is using differential forms. Now I know you're still a little bit green on differential forms, but this is a really simple example. So a really simple use case. We're just gonna use a differential one form, which is nothing but a covector field. Okay, so we take a look at x and y, and what we are trying to do is we are trying to come up with a differential one form that annihilates them both. Okay, so the appropriate differential form would be, so we guess omega is equal to x, so x dx plus y dy minus z dz. So in this way, omega is a differential form that annihilates both of them, right? Because using omega on the vector field x gives us x times z minus z times x, and this is 0. And similarly for the vector field y, right? So we guess that we guess a differential one form that annihilates it, and we are searching for And now omega on x is equal to 0, omega on y is equal to 0, right? So that d is equal to the kernel of the differential form omega. Okay? Now we seek a function f that goes from M into R such that omega is equal to the total differential of f, right? So now it's really straightforward to come up with such a function. Again, we guess that this function should be given by xyz is equal to x squared plus y squared minus z squared. Okay. I may also multiply everything by a half so that indeed we will have omega equal to df, right? So maybe, but this is irrelevant. So we have this. Now, the integral manifolds of D are given by level sets of F. And why does this hold now? Why are level sets even submanifolds in M? Does anybody reckon?
Is it because it's smooth?
No. Smoothness is obvious.
F
Because
is, oh, I don't know, the derivative is non-degenerate.
Yes. So that would be the argument that so F is a submersion on M. Okay. So for an appropriate choice of C. So of course, f to the power of -1 of C, so the preimage of C is now a submanifold in R to the power of 3, right? But we have to kind of be a little bit careful because we need to like restrict it only to our M, right? We have to take the intersection of this pre-image with our manifold M. Okay, so this, but that's all essentially, because now you have that df is equal to the total differential, right? This is nothing else but x times dx plus y times dy minus z times dz. And since d is equal to the kernel of this differential form, you are done. You have nothing more to check. So and note that these are these submanifolds, right? This pre-images of C or f to the power of -1 of C for C something maybe arbitrary. These are hyperboloids. So if you were to maybe let me show you a picture or two. Okay, I have to stop streaming this screen here so that I can show you can you see anything?
Yes.
Okay, so this is an example of an integral manifold of our distribution D. This dark blue stuff, this is so for some choice of C, we get this integral manifold, and you will see that I have here also written like an integral curve of a vector field. This now here, this these lines correspond to one of the two vector fields. I'm not sure, I can't recall which one I drew. Was it X or was it Y? But this now is like an integral curve of your vector field, X or Y, I'm not sure, that also passes through this integral manifold of this distribution. Okay, so this is now the intuitive the intuition behind this exercise. So also we have another example. Another example is this. This is just for a different choice of like of the number C which we're taking. Okay, so but note that we're limiting ourselves to Z greater than 0, so that we have like simplified calculations. We can divide by Z, etc. So that you should only like look at everything above the Z equals to 0 plane. Okay. Okay, so let me conclude this exercise and then we'll make a break. Like the second way of solving it would be using the proof of Frobenius theorem. So the Frobenius theorem kind of gives us a recipe on how to find the integral manifolds of our distribution. Okay, so but it's a little bit more tricky. Like this what we've written above, we had to guess something, so it was tricky in a certain sense. But now we have to, so for the second method of finding the integral manifolds, we have to do a lot more work, but a little less guessing maybe. So the proof goes as follows. First, we take the vector field partial z, which is complementary to D at any point. So this would mean so dp direct sum and ln partial z at p is equal to dp r to the power of 3. Okay, this is what we mean by complementarity. Okay, first we take this vector field, and so we notice that the projection from r to the power of 3 to r to the power of 2 that takes a triple xyz and gives us back xy, induces an isomorphism so d pi at point P goes from dp into what tp r to the power of 2. Okay, so this is the differential of the map pi, but restricted to our distribution. So this is by complementarity of the vector field partial z to our distribution D. Okay, this is the first step. Okay, the second step is that we find local sections V and W, let's call them, of D, such that they are pi related to partial x and partial y. Okay, does anybody see what these local sections V and W would be? So if we scroll a little bit upwards,
maybe if we add the appropriate multiple of dz.
Sorry.
If we add the appropriate multiple of dz so that it gets annihilated under the projection. I don't know, just like plus x over z dz.
Partial z will be annihilated with the differential of pi anyway, right? Because we're just taking the projection onto the first two coordinates. But take a look at, take a look at our definition of x and y. They're here, right? If we take the differential of our map pi and use it on x, for example, okay, sorry. This term will definitely fall away because it's just a multiple of partial x. Okay, well, how about this one?
You mean because it's a multiple of partial z that will fall off?
Yes. Well, how about for the first term?
We'll get z, I guess, maybe.
Sorry?
We'll get z.
Why?
Because that's, I don't really know.
No, we won't get z. We will get the same term. We will get z times partial x, but we want to get only partial x. Okay? Because that means that's what it means to be pi related to partial x. So what do I have to do? I just have to divide x by a function z. Okay? Take v is equal to partial x plus x over z partial z. So this is equal to 1 over z times x, and we take w equal to partial y plus y over z partial z, and this is 1 over z of the vector field y. Okay, so, and now, since partial x and partial y commute, by the result on the commutator and relatedness, we also get v comma w is 0. And this is crucial. It's crucial that we get this commutator equal to 0. Okay? And why is it crucial? Because now not only these vector fields v and w commute, also their flows commute. Okay, so and if their flows commute, we may form a composition of their flows. And that's precisely the content of Frobenius theorem. You make exactly what we're doing here. Okay, so we are doing now the proof of the Frobenius theorem, but on a specific example. That's all we're doing. So now the third step is to find the flows of v and w, and so we're not going to do this. This is left for you as homework because it's really simple. So phi t v of x, y, z, I'm just going to write it, what we get.
So if isn't the theorem about pi relatedness just saying that since pi v and pi w so the commutator of pi v and pi w is 0. So the commutator of v and w is in pi relation with 0.
Yes.
So it's
0.
so the commutator of v and w is in the kernel of d pi. So that means it's just vertical. It doesn't actually mean it's zero.
Okay. Okay, it's vertical. But at the same time, X and Y, like these are in involution, right? So they have to be in D. So it has to be in D, and at the same time, it has to be in the linear span of partial Z.
Yeah.
Right?
Okay. Yeah.
So but these two things are complementary. So hence their intersection is the zero vector.
Okay.
Okay, so now I'm going to write only the flows of V and W. This is left for you as homework. This is really simple to calculate. It's like it takes 5 lines or something like that. I mean, if you've had your systems of ODEs course. So these are the flows that correspond to our vector fields. And now we form the composition. So we actually define a map phi of u comma v comma oh sorry, I'm going to have to write some different letters here. V comma w comma u, for this to be simple to read. That's the only point of it. V comma w comma u are the arguments of this function. So, and we define it by the composition of the above flows, and we plug in 0, 0, u. And this is 0, 0 here is why are we plugging this point into this composition? The reason behind it is that we are we are looking for in a way defining functions that are going to I'm not sure how to say this. We are looking for a chart for r to the power of 3 or m, such that it will be centered around this 0. Okay, but this defining property of this chart will only be its last function, as we will see. So I'm not sure if I'm making any sense here. Just write these zeros here, and if you want to, you can try to plug in like say an arbitrary point x0 and y0 and see what happens. This is like it's a little bit complicated to explain why we're plugging zeros here. So what we get now is phi v. And now what do we get if I plug 0, 0, u inside the flow of the vector field W? Yeah, well, we get nothing else but 0, w, square root of u squared plus 0 plus w squared. Okay, and now we have to plug in this triple to the flow of the vector field V. And what do we get? V comma W comma and U squared plus W squared. That's the first stuff, and then plus 0. This 0 comes from the 0 in the first place of this triple. And in the end, we also get V squared. Okay. So now what we have to do is we've actually defined a chart here, and we have to like take a look at its inverse. That's the content of Frobenius theorem if you've read it and understood it. So what we have to do is we equate this by x, y, z, so that we have v is equal to x, w is equal to y, and z is equal to the square root of u squared plus w squared plus v squared. Okay, so from this, what I get is u squared is equal to z squared minus w squared minus v squared, and this is nothing else but z squared minus x squared minus y squared. Okay. So now the integral manifolds of D are level sets of the function u, which is just the square root of z squared minus x squared minus y squared. But the level sets of this u are nothing else but level sets of f, right? And you may check that indeed the kernel of this map u is precisely the distribution in question. Okay, so we have two different recipes on how to find the integral manifolds. One is this long and convoluted way with computation of flows. And the first one is just by trying to figure out which differential form annihilates your distribution.
So here, did we miss all the integral manifolds that, you know, have a hole in the middle?
What do you mean by a hole in the middle?
Yeah, well, we have, you know, kind of two types of hyperboloids that have two sheet and one sheet, and then the one sheet hyperboloids go out from some radius. They don't actually go to the center, right? The image you showed before had two cases.
Okay. I mean, the image I showed before had two cases, and we get these two cases. We also get the case where we just get a cone. That's also a hyperboloid, right? So, I mean, it's just a special kind of a hyperboloid. This is the level set of 0, right? We get all of these. We didn't miss any one of these three integral manifolds.
But didn't we assume that we started at the point 0,0 u, which automatically means that we missed all the ones that don't go through that point?
Yeah, well, is there a hyperboloid that has 0, 0, 0 as its point?
Well, the cone, but they're also, I mean, it's a singular point, right? But
Yeah, it's a singular point. The cone is not a submanifold at that point. That's why we're limiting ourselves to this manifold M, right? To this z greater than 0.
yeah.
Because at that point we would have problems. So that's precisely why I just simplified this mission by only taking the z greater to 0.
Yeah, but so we did still miss the cone, right? Because then it has no point at all with 0,0 u.
No, we didn't miss the cone. We still get the cone.
Yeah, I mean, you can see at the end where you get this nice polynomial equation that if you look at all the solutions of that, you also get all the other hyperboloids. But my point is that if you just solve the differential equations, you're missing out a bunch of them because you just don't have the 0,00 u on half of your hyperboloids.
Yeah, well, but that's okay, isn't it?
Yeah, well,
0,
it's not
0
wrong.
u, for u greater than 0, we get an integral manifold through that point.
Yeah.
But we don't get an integral manifold through 0, 0, 0, which is okay.
So we have to be more, in general, we would have to, like, if we didn't have this nice geometric interpretation, we would like have to be very careful that we actually exhaust all possibilities, right?
Yes. I mean, this is like something that if you have a geometrical picture behind the happening, it's really much more convenient to do these calculations because you know which points you're going to miss, etc. So all of these calculations are so you're gonna have to be careful when doing this, right? There's I mean, there's a reason it's called a theorem. There's a reason it's called Frobenius theorem. It's profound. So the specific examples that we do are going to be at least as complicated. So, but this is more or less the only example that we'll do. So yeah, I suggest we make a 5-minute break at this point. I've completely forgot about the break. All right, so let's continue. If you're here, before we go on to tensors, there's this example that I would like you to do as your homework. So so if G is a Lie group and H is a Lie subgroup of G, define f of the Lie algebra of this H at point X to be d of Lx at the identity, so at the neutral element of H. Okay, so homework for you to do is f of H is a distribution of G and which is integrable. Also, its integral manifolds are given by the left cosets. X times H, which is equal to left multiplication, or the image of the left multiplication by X of the submanifold H. So this is your homework. We won't lose time anymore with the Frobenius theorem because we're moving on to tensors. So this introductory part of this section, it's meant for those who aren't accustomed to tensors yet. So for those who haven't had much experience with computations, with tensors, etc. So let's first define a tensor product of two vector spaces. So given vector spaces V and W, we form the vector space V tensor W. So does anybody know how we do it? What is its construction?
We take the basis of the first one and the basis of the second one, and the basis of the tensor product of both of these spaces is made out of all possible tensor products of the bases.
Okay, but what is the tensor product then?
Like concretely or theoretically?
Theoretically.
It's something to do with where we have the Cartesian product into the tensor product, then into something else, then we only have one map defined, something like that.
Yeah, exactly. But you know, if you write the tensor product of two vectors before you make the tensor product of two vector spaces, you're going to end up confusing people because nobody knows what that symbol means. So that's why we are defining this maybe a little more abstract vector space first. So we define f v comma w by g, where so first of all, f v comma w is equal to a sort of linear combinations of pairs so now an is in the field, the underlying field of v and w. N is just a natural number, and Vn is from V, Wn is from W. So this is the vector space generated by pairs. Okay, so these are sort of yeah, linear combinations that are, you should keep them in mind as formal. So for mathematicians, this is just the free abelian group generated by v times w, so generated with the Cartesian product, right? The free abelian group over our field. Okay, so this is first of all, and second of all, we have that G is the subset of F so subset, maybe I should write here in place of subset vector subspace. Generated by elements of the form so 4 types. One is V1 plus V2, comma W, minus V1, comma W minus V2, comma W. That's the first one. The second one is V, comma V1 plus W2, W1 plus W2 minus V, comma W1 minus V, comma W2. So then we have alpha V, comma W minus alpha V, comma W, and for the last one, V, comma alpha W minus alpha V, comma W. So, and note that this is really important. This sum here is something completely different than this sum here. Okay, the latter is the sum, is the plus, is addition in the vector space V, but the above, so the former, is like this abstract sum that is the formal linear combinations. Okay, so we have the map pi that goes from V times W into V tensored W, that's given by the composition V times W goes into F V times W. So this is just the inclusion. The first map is just the inclusion, and the second one is the projection into F V W over G. So this, of course, this is defined as V tensored with W. Okay. So, and we denote V tensor product W is equal to pi of V, comma W. So this is the symbol that was discussed earlier, the tensor product of two vectors. Okay. And now, so what does this serve us? The notion of the tensor product captures the essence of multilinearity of maps V times W into an arbitrary vector space U. So multilinearity, what is meant by multilinearity is so phi of alpha V1 plus V2 comma W is equal to phi, alpha of phi of V1 comma W plus phi of V2 comma W. And similarly for the second argument, right? So why does the notion of the tensor product capture the essence of this so-called multilinearity? Is because of the universal property. Okay, and the universal property says that, let's write a diagram on the left and we'll write something on the right. So for any vector space U and a bilinear map phi that goes from V times W into U, there exists exactly one linear map phi bar that goes from V tensor product W into U, such that, of course, we have to have phi equals to phi bar of pi. Okay.
In other words, the graph commutes.
Sorry?
In other words, the graph commutes.
Yes. So this universal property is what encapsulates what we've written above, that the tensor product captures the essence of multilinearity. Okay, so proving this is a sort of triviality, but it's an abstract triviality. Okay, I'm just going to write the idea. I mean, the formal proof is not really all that harder, but I'm going to be a bit sloppy here in the argumentation. You may find these proofs are everywhere of this universal property of tensor product of vector spaces. So what do? We have the map phi, we extend it to a linear map. Let's call it phi tilde. So what is its prescription? It's just it's really straightforward. So you take an arbitrary linear combination from the definition of f, v, comma, w, and you do this map phi, you do it term-wise. So again, this sum here is something abstract. This sum here is the sum in U. Okay. So first we extend this map phi to phi tilde, and then there holds phi tilde of, let's take the first identity here. Okay, let's take this one, see what happens to it when we map it with phi tilde. So this is v1 plus v2 comma w minus v1 comma w minus v2 comma w. Okay, so this is now by definition of phi tilde. This is phi of v1 plus v2 comma w minus phi of v1 comma w minus phi of v2 comma w. And now we use multilinearity of phi to put all of these terms together, and what we get is phi of 0 comma 0, and now this has to be 0. Okay. So hence yeah, and let's write similarly for the points 2 to 4. And now what we get is that G must be a subset of the kernel of, phi tilde. Okay. So F tilde descends to a well-defined map this is not F, I'm always writing F. This is phi tilde. Phi tilde descends to a well-defined map phi bar that's defined on this pairs V tensor product W as F tilde of V comma W, which is again I'm writing F. This is phi of V comma W. Okay, so this is the idea. How do we prove the universal property? Like, as always, the uniqueness is the easy part of the proof, and the existence is a little bit more tricky because it's abstract, and this is the existence part of the proof. Okay. So let's have an exercise, an abstract exercise, in order to see if we indeed understand like this notion of a tensor product. So prove that the set of all homomorphisms from V to W is isomorphic to V star tensor product W. Any ideas on how to prove this?
Are these finite dimensional?
Yes.
Okay, then maybe just, you know, do the so the kind of construction where you take a vector times a functional, in the sense that the functional acts on a vector, spits out a number, and then you multiply the vector by the number.
Yes, exactly. So define, let's say, psi that goes from V star times W into homomorphisms from V to W by, so this is a functional now, okay? So this is a thing from V star. Okay, so we take such a simple tensor, right? This is just yeah, a pair f times w. That's what it means to be a simple tensor. We don't have a linear combination of different tensors, okay? Okay, and where do we map it? We map it to a homomorphism that sends v into f of v times w. So that's how we define our map. And now we have to check a couple of things, right? We have to check that this is indeed a homomorphism. So also we have to check well-definedness, right? In the sense that this is indeed a homomorphism, like the right-hand side of this equation that's definitive for psi, that this is indeed a homomorphism. That's what we have to kind of check, right? Well, this is, I'm just gonna make a tick here because it's obvious that if we have a linear functional f, then of course if we're gonna plug in v plus v2, it's gonna end up being f of v plus f of v2. Hence, we're getting the desired thing that needs to be satisfied for in order for this thing to be a homomorphism, right? So that's well-definedness. Another thing would be that psi is a homomorphism. Right? So we would have to take what? We would have to take an arbitrary linear combination of such tensors and see what it happens with them, right? But we are defining our psi on simple tensors, which means that I haven't written it here, but I should write here and extend by linearity. So this, again, this is automatically fulfilled because we're just extending by linearity.
So this thing with well-definedness, right? Usually, if I understand it correctly, this problem is that we are saying psi is defined on simple tensors, but simple tensors aren't unique objects in the sense that, you know, you can pick different f and w and get the same thing. So if I think the usual way would be to actually define a map psi not on the tensor product, but on the Cartesian product of v star times w and check that it's bilinear, and then use the universal property to descend it. So that would be well defined.
Yes, that would be, but well-definedness, as I've said it here, it's not to check. I mean, it's not the thing that you were talking about. It's just the are we mapping into homomorphisms?
Oh, okay.
So I didn't ask myself whether or not this is well defined in the sense of every you know, every member of an equivalence class gets mapped to the same thing, yada yada. This is also something that we would need to check. Okay, so indeed you're right. We would have to define a map on the Cartesian product, check that it's bilinear, and then conclude that psi, as we have it here, is indeed like defined by the map on the Cartesian product. Okay, but it's obvious, right? Isn't it? That the map, if we define psi of f comma w and send it to the same element as we set here, that thing is bilinear, right? Isn't it?
Yes.
So everything here is, as far as tensor products go, you just have to keep in mind that everything is trivial but abstract. So that in the end, you only have to kind of, just use the fact that we have this universal property that captures the multilinearity of everything. Okay, so let's check, for example, injectivity of psi. Okay, so for example, let's have f of w mapped to 0, so to the trivial homomorphism, right? This means that f of v times w is 0 for any v in v. So this means that either w is 0 or f of v is 0 for any v in v. But this now implies that f tensor product w must be 0. So that the kernel of this map, psi, is trivial. Okay. How do I conclude from this that psi is an isomorphism?
Well, if it's injective and linear, then it's automatically an isomorphism in finite dimensional case.
Okay, so in order to use that argument, we have to know the dimensions of hom v comma w and v star tensored with w, right? So, but using a basis for v and w, we may identify hom v comma w with the set of all, let's say, m times n matrices, which is an dim v times dim w dimensional vector space, right? Okay, but now this thing here is the same as the dimension of v times w. So, but why is this true? So this is again something for you to check as homework. So this is something that has been said already today. If vi goes from 1 to dim v, and wj, j runs from 1 to dim w, are bases for v and w respectively, then a basis for v tensor product w is given by vi times wj, where I runs from 1 to dim v, and the j runs from 1 to dim w. So this is something for you to check. This is homework. And the consequence of what we've written here in red is exactly that, this equality of dimensions, right? So if we have this plus injectivity of psi implies
And the dual of v has the same dimension as v.
yes. Yes, this is a finite dimensional setting, right? So everything is well behaved here. Okay, so I hoped that there would be more time for us today, that we could start doing symmetric and alternating tensors, and make a pathway towards the metric on a smooth manifold, so towards Riemannian geometry, but I reckon that we'll have to do that next time. Do you have any questions? Everything is clear as day. Nothing is clear as day.
Well, tensor products are clear.
Yeah, tensor products are clear, I reckon, for mathematicians. For For physicists, I'm not sure how much they've worked with them. So this is the reason why we're doing this, because maybe not all of us are comfortable with tensor products. Yeah. So multilinearity is something that will keep appearing from here on. For example, the scalar product, so the inner product, this is a bilinear map. The determinant map is multilinear. Matrix multiplication is bilinear in both arguments, right? In the left matrix and in the right matrix being multiplied. So this is now a concept that will be crucial for our further exercises and lectures. So bear in mind that you have to know them and feel these concepts really well. Let's conclude this exercise session, and I'll see you next Friday.
Goodbye.
Goodbye.
Ciao, ciao.
Bye.